So in the last lecture, we took a look at line modeling using lumped parameters, where we basically modeled all the line elements as discrete resistance, inductance, and capacitance. This time we're going to take a look at distributed parameter line modeling, where we basically model the effect of the distributed inductance and capacitance of the line. And you may or may not have seen this before. Sometimes this is covered in undergraduate electromagnetics classes. And so for this particular class, we're not going to get into a lot of the depth on the theory. Mostly I'm just make sure you guys kind of know some of the basics of the modeling. It's a kind of a complicated subject area, and we're just going to be scratching the surface here. But hopefully you get enough from this where you kind of understand how the modeling is done in programs like PS-CAD. And so I'll talk about the theory first, and we'll get into what we call the transmission line equations, and then we'll get into concepts of reflection and refraction. And then the way we're going to analyze this by hand is we're going to use something called lattice diagrams. There's different names for this, but I refer to this as a lattice diagram. I'm also going to touch upon how we can take the single phase model and extend that to three-phase modeling, but we won't be able to get into a lot of depth on that particular subject. For the second part, for part B, I'll go through a couple worked examples so you see how this gets applied, and we'll focus on single phase modeling in this case. And then for the EMTP modeling, I'll kind of show you how this kind of maps into PS-CAD, and also show you how you can set this up for doing three-phase examples. So for the pi equivalent model, basically this will be okay if we have like short line lengths, and if we have just something on the order of like a few miles or so, this will be okay. However, this isn't really accurate for longer length lines, or when we're looking at high-speed transits, such as that due to lightning or line switching. And so, like I said before, we want to consider the inductance to capacitance is actually distributed instead of just simply going to be lumped. And the way we're going to do this is we're going to look at voltages and currents on these lines in terms of traveling waves. These waveforms are going to be traveling close to the speed of light. And this theory has been around for a long time. I mean, this is basically the theory that was developed to analyze undersea telegraph cables, which is why they're sometimes referred to as the telegraph equations. So the way this is going to work is what we'll be doing is we'll be doing our modeling in terms of this differential line segment. In other words, if I just took a small section of line and say it has a length of delta x, and where delta x is going to be very small, it would have a series inductance and would also have a shunt capacitance. Note what we're going to be doing in this case is we're going to be ignoring the resistance. So what we're going to be looking at is what sometimes referred to as a lossless case. So we'll add resistance in later on. But we're going to be assuming that basically if you just look like a very small chunk of line, that it has this series inductance and has this series capacitance, where L and X are values in terms of, you can think about it in terms of like inductance per length. And so if I had the small differential distance I'm analyzing, then the net inductance is L times delta X, and the net capacitance is C times delta X. On the left-hand side, we've got a voltage and we've got a current. And then basically when we account for the voltage drop, then the voltage at the receiving end is going to be V plus delta V. And then when we account for the current that's being injected by that capacitance, then the current at the receiving end is going to be I plus delta I in this case. So when we write the equations out, what we can do is we can start off by writing equations that are differential equations. Basically, that change in voltage, or actually minus the change of the voltage because of the way I oriented the direction of x, is going to be the inductance times the change in current with respect to time. And then as delta x becomes small, and the limit as delta x becomes small, basically what we're going to have is we're going to have partial derivative equations, right? So we can talk about a partial of v with respect to x being equal to minus L times the partial of I with respect to t. We can write a similar equation for the current, where eventually, if we look at as delta x becomes very, very small, that what we're going to have, sorry about that, what we're going to have is we're going to have this particular equation. Let me go ahead and just check my pointer right here. What we're going to have is we're going to have this particular relationship right here, where the partial of I with respect to x is going to be minus c times the partial v with respect to t. Okay, so we're going to start off with these two partial differential equations. Now, if you do some math manipulation on this, and I'm going to post some notes on the Moodle site that goes into this in a lot more detail in terms of what equation gets substituted in what equation, you're going to end up with two second derivative expressions. Second partial of v with respect to x is equal to minus L times the second partial of I with respect to x and t. You've got an equation 6, which is second partial of I with respect to x and t, which is minus c times the second partial of voltage with respect to t to the 2. And if you substitute 6 into 5, what you come up with is this very famous first equation, which basically what it's doing is relating the second partial of voltage with respect to position x is going to be L times C times the second partial of voltage with respect to time. Okay, so this is the first of the two telegraph equations. If you write similar equations for current, you're going to get equations 8 and 9, and if you do some math substitutions, you get the second telegrapher equation, where basically what you're going to have is you're going to have this second partial of I with respect to x equal to LC times the second partial of I with respect to t. So the two key relationships are 7 and also 10. Okay, those are the terms we're going to be interested in taking a closer look at. It turns out if you play around with these two telegrapher equations, and if you think about what's going to be the solution, it turns out that the solution for current is going to have the form of a function f1 with the argument x minus, I'm going to call this vt, plus f2 with an argument x plus vt, where it turns out that v is equal to 1 over the square root of L times c. And the reason I'm using v is v is going to turn out to be a velocity term. All right, so if I substitute I as this function of f1 and f2 into my telegrapher equation, I'm going to find out that this is basically going to work. And if I substitute that 11 into equation 10, basically what I'm going to see is this partial v with respect to x is going to eventually be equal to minus L times this partial of f1 with respect to time plus this partial of f2 with respect to time, which is going to be equal to L times the velocity term times in brackets this derivative of f1 minus this derivative of x2. And so this little prime sign in this particular case right here, what that does is that refers to taking a derivative. So if I integrate both sides of 13 with respect to x, then what I can show is this voltage is going to be the inductance times the velocity term times in brackets f1 minus f2. And if velocity is 1 over the square root of LC, then basically L times the velocity is going to be equal to the square root of L divided by C, which is our characteristic impedance term. We've seen this before. This shows up quite a bit, where what we're going to have now is we're going to have this kind of like this key term, which we're going to see over and over, which is the square root of L over C. And so basically, if this was kind of the form of our current, if our current, had an F1 term and an F2 term, it's just not cooperating with me right now. But this current had an F1 term and it had an F2 term. then basically that's going to relate to voltage by the characteristic impedance. And you can see in that first term it's a positive impedance, in that second term it's a negative impedance. So what's the interpretation of what F1 and F2 represent? Well, let's say we plot F1, and let's suppose it has like a triangular shape associated with it. At x equal to 0, what we're going to have is we're going to have this triangular shape at time equals 0. And if we look what happens at a later time, if we say plug in for t equal to tau, basically what we're going to have is we're going to have that same waveform shifted over to the right at position x equal to v times tau. All right. So the interpretation of this is basically what we have here is we have a waveform, that triangular waveform, which is shifting to the right at a velocity that's given by 1 over the square root of LC in this direction of increasing x. All right. So basically what we have here is we have kind of like a traveling wave. Whatever we have at time equals 0 gets translated down this line where it's at this position x equal velocity times the tau term, the delay term, just shifted over to the right. All right. So anyway, we have the forward traveling term, that's the F1 term. It turns out that F2 x plus vt, that's going to represent a waveform that's traveling to the left, that same velocity 1 over the square root of L times c. Okay, so what we have in this case is we have a forward traveling wave and we have a backward traveling wave. The forward traveling wave is given by the F1 term, and the backward traveling wave is given by the F2 terms. And again, what's interesting about this is for the forward traveling wave, the voltage and current are related by positive characteristic impedance, and for the backward traveling wave, it's related by a negative characteristic impedance or surge impedance. And if we have a lossless line, basically the shape of this waveform is not going to be impacted. What we're going to see basically as this wave travels from the left to the right, there's no attenuation, there's no distortion. Now in a real line, this is going to get distorted and attenuated, the magnitude is going to drop. But if I don't have any resistance, this line is going to be lossless. All right, so basically the shape's going to stay constant. Now, one thing we need to take a look at is what happens is if I have two cables or two lines put together. And this is a very common type of thing where what we're going to see is we're going to see two cables put together, and the point where those two cables connect together, that's going to be referred to as a discontinuity. And so we have to have a way of dealing with that. All right. And so let's suppose we have a wave, and let's suppose it has an amplitude of V1 and it's traveling from left to right, and that first line has an impedance of ZA and that second line has an impedance of ZB. What's going to be happening as that waveform travels from cable A or line A to line B? Well, what's going to happen is there's going to be this discontinuity, and we got to kind of figure out what we're going to have that's going to continue to travel down line B, and then what are we going to have as far as the reflection that's coming back on ZA. Okay, so the forward traveling wave, there's going to be a relationship between voltage and current, which is given by ZA. What we can say is we can say I1 is equal to V1 divided by ZA. At the discontinuity between the two cables, what we're going to get is we're going to get a reflected wave, all right? And so that's going to be given by V2 and I2, and we know that that's going to be related by minus the surge impedance of line A. And then we're going to have that wave that's going to continue to travel to the right on that line B, and the relationship between voltage and current is going to be such that I3 is equal to V3 divided by ZB, all right? So subscript 1 represents the original forward traveling wave. Subscript 2 is going to be the reflected waveform, and then subscript 3 means is representing the refracted waveform that's actually going to continue to travel down that second line segment B. All right, so in order for the math to work on this, we're going to have boundary conditions that are going to be met. And then basically at that discontinuity, we know that the voltage of the forward traveling wave, because the plus the voltage of the returning wave, is going to have to be equal to the refracted waveform. And then also, as far as the currents have to add up as well, that I1 plus I2 is equal to I3. And so if we substitute in for V1, V2, and V3, basically we can do some math manipulation. And what we're doing with this math manipulation is we're trying to figure out what's this going to mean in terms of what's going to be, first of all, the reflection at that point of discontinuity. And so that's going to be a term I'm just going to refer to as gamma A. A represents the fact that it's a reflection. And it turns out, if you go through the math on this, the ratio between V2 and V1 is going to be ZB minus ZA divided by ZB plus ZA. In the limit, if ZB is really large and ZA is small, this reflection coefficient is going to be 1. However, if ZB is small and ZA is large, this reflection coefficient is going to be minus 1. And so this reflection term can vary between 1 and minus 1. As far as what's refracted in terms of how much of that original forward traveling waveform gets onto that second cable section B, then what we're going to need is what's called a refraction coefficient. And if you go through the math in this, what you could see is that this refraction coefficient is going to be the ratio of V3 to V1, which it turns out to be 2 times ZB divided by ZB plus ZA. So what values can we have for this refraction coefficient? Well, if ZB is really large with respect to A, this could actually be 2. If ZB is really small with respect to A, this could actually go all the way down to 0. And so the refraction coefficient can vary between 0 and 2. Okay, so let's apply this to a step function that's basically a flat wave. We have the square pulse that's traveling from left to right. It's traveling down the first line section A. And then basically what it's going to do, it's going to hit a discontinuity. And once it hits that discontinuity, we're going to get a reflection and we're going to get a refraction. That reflection is V2 and that refraction is V3. The amplitude of the reflection is going to be such, V2 is going to be such that that's going to be gamma A times V1. And what we're going to need to do on the left-hand side of the discontinuity in order to figure out what the net voltage is, we have to take V1 plus V2. So as soon as that V1 hits that discontinuity, then in order to do the math, we have to add both those waveforms up. All right, so that's going to be the reflection part of that. And then what we're going to have for the refracted part, the part V3, then this is going to be given by the refraction coefficient times V1. And so if we have that waveform V1 traveling from left to right, as soon as it hits that discontinuity, and what keeps traveling down that second cable section is going to be V3, which is gamma B times V1. All right. And what's going to happen when V3 gets to the end of line section B, it's going to hit another discontinuity, which is going to cause another reflection. And so this is kind of a really turns into kind of like a bookkeeping problem as far as having these waves bouncing back and forth, because basically the effect's going to be additive. And so as the reflections keep happening, we have to kind of keep up with this in a bookkeeping way. All right, so just as a quick example how this could be applied, let's suppose we have an overhead line impedance which is given by ZA of 400 ohms. This would be kind of typical for overhead. Hundreds of ohms, 300, 400, 500, 600 ohms. we have a surge with amplitude 300 kilovolts and it's traveling down this overhead line, it's going to be hitting a cable. And so that's going to be the discontinuity we want to model. Cable impedances have characteristic impedances like 50 ohms, 75 ohms in that region, so smaller than overhead. So we want to know, well, how much of this surge is going to find its way into the underground? And so for that, we need a refraction coefficient. So the refraction coefficient is 2 times the characteristic impedance of B divided by the sum of the two characteristic impedances. 2 times 50 over 50 plus 400 is 0.22. And what this means is we're going to have 0.22 of that 300 kilovolts, which is 66 kilovolts, continuing down the cable. Okay, so this is a very practical problem, because if we have a lightning strike that hits overhead and there's a transition between overhead and underground, then we're going to be concerned with how much of that surge voltage actually gets into our cable, which would be more susceptible to overvoltages. Now, what would happen is, instead of having that cable, that instead we had an open circuit. What difference does that make? In that case, the surge impedance is infinite. And we're going to get a reflection coefficient of 1 in that case, and a refraction coefficient of 2. So basically, there's a couple ways you can think about this. Is basically, if I've got that surge coming down, and that surge has this voltage of 300 kV, what keeps traveling into that open circuit basically is going to be 2 times that value. So we could either take the refraction coefficient and multiply that by 2, or what we could do is we can say, hey, this is going to reflect 300 kV. You want to add up V1 and V2, that gives me the 600 kV. It gives me the factor of 2 still. But basically what happens is, whenever I have a waveform traveling down a line and I hit an open circuit, I get a voltage doubling effect. And so this is why a lot of times we would put some type of surge arrestor at the end of the line to prevent the cable from getting damaged in this case. All right. So now, as far as doing the bookkeeping, we need a tool in order to do the calculations if we want to do these calculations by hand. And that would be through the use of what I refer to as a lattice diagram. Pulse bounce is another word, Bewley diagram. There's a lot of different names for this. But basically what this does is it's used to track the forward and reverse backward traveling waves. And this is sort of characterized by the time it takes for this waveform to go down a line segment. And so we will work with tau, which is the time it takes for this traveling wave to go down the line. If you have the velocity of 1 over the square root of LC, then that tau time is line length divided by velocity, which turns out to be length times the square root of LC. So in the lattice diagram, what we're going to have is we're going to have a diagram where position along the line is going to be horizontal, right? So this is the beginning of the line, this would be the end of the line. So if I have a line of a certain length, what I can do is I can track what's going on during the entire length of that line. Time is put on a vertical axis going down. And so what I would do is I would set my time axis up in terms of time 0, the time it takes to get down the line segment, 2 tau, this is the time it would take for the pulse to go all the way down the end and back. Then I could have 3 tau, 4 tau, 5 tau, and 6 tau. And what I'll do is I'll usually put little dashed lines on here so I can kind of track what's going to be the magnitude of the waveforms. And let's suppose I got a waveform injected into this line with amplitude or magnitude of V1. I've got a reflection coefficient gamma A1 on the right. I've got a reflection coefficient of gamma A2 on the left. The subscript numbering has to do with what reflection coefficient I need first. And so if I have V1 traveling to the right, it hits the discontinuity with reflection coefficient of gamma A1. And what gets reflected back is gamma A1 times V1. Now, the net voltage I'm going to have at a given time, I'm going to have to add these voltages up. All right, so as soon as V1 hits the right-hand side, hits this end, then basically have to add the V1 plus the gamma A1 plus V1. Now, I get a reflection going back, gamma A1 times V1. It hits a discontinuity on the left-hand side, defined by a reflection coefficient of gamma A2. And then when I get reflected back is going to be gamma A2 times this, or gamma A2 times gamma A1 times V1. And then this goes back toward the right again. It gets reflected again by this coefficient. And you can see what's happening here as I go back and forth, back and forth. Then what can happen is either maybe this waveform rises or this waveform is going to tail off. But depending on where I'm at, what I need to do again is I need to add all these waveforms up. So at this particular point here, I've got V1, but as soon as I've got the waveform return, I'm going to have to add gamma A1 V1 plus gamma A2 times gamma A1 times V1. All right. So you have to basically add everything up, and we'll go through some worked examples where you see how this would actually get used then. All right. Now, there's a few things you got to know when you're working with these lattice diagrams. One thing is how to model a source. So let's suppose I had a voltage source on the left that's injecting this transit waveform. Well, the way we model that, we just use a Thevenin equivalent. Let's suppose the source had a Thevenin equivalent impedance given by RS. Then basically what we have as far as V1 being injected into the line, if Vs is the source voltage, is we basically have a voltage divider. So Z0 divided by Rs plus Z0 times Vs gives us what gets injected into V1. And so this is actually something else we have to make use of as well. Now, if we're talking about what's going to be the reflection coefficient when we have a traveling wave going back toward the source again, then we just simply use the source impedance. And so gamma A, this reflection coefficient at the source end, would be Rs minus Z0 divided by Z0 plus Rs. So those are usually the only things you need to worry about, as far as modeling sources and energizing sources and things along those lines. Now, what would be different if we were talking about three-phase? And I'm just bringing this up because when you do simulations, you're doing three-phase sections. I'm not going to expect you to do three-phase problems by hand because those are rather difficult. But if we have three-phase, then basically we've got three line elements with inductances and capacitance. But now what we have is we have mutual inductances like LAB or LBC between these line elements. We've got mutual capacitances between the line elements, and we have capacitance with respect to ground. So basically these are the same inductance and capacitance terms that we would calculate for lumped lines. Is the same ones we were calculating like in the last lecture, except now they're going to be applicable to three-phase distributed parameter modeling. And so these capacitances would be in terms of like inductance per meter, inductance per kilometer, inductance per mile, whatever. But these would be per unit lengths then for this particular model. And so when we do the modeling on this, everything's got to be done in terms of three-phase. And what this means is that this inductance and capacitance would not just be a single term, it would actually be a matrix. And for a three-phase system, we could boil this down if we reduce out the neutral wire. We could boil this down to a 3x3 inductance and 3x3 capacitance matrix. And again, we're just talking about the lossless case. So inductance would be in henries per meter and capacitance would be in terms of farads per meter. So for currents and voltages, these currents and voltages would be a function of position along the line. They'd be a function of time. Now we're going to have three-phase, phase A, B, and C for current, phase A, B, and C for voltage. And so these are going to be 3x1 terms. And all those equations that I wrote before are still applicable, except now these partial terms are you have a 3x1 voltage on the left, you have a 3x1 current on the right. This inductance is going to be 3x3. But now everything's going to have to be three-phase. So you can see how complicated this gets because if you're solving, you don't really just have one single phase line equation to solve. You got three coupled single phases to solve. So it makes it a lot harder to solve this directly. There's be a lot of computation associated with this. So how do we deal with this? Well, the way we would deal with this is the same way you would do kind of like fault analysis and use symmetrical components. You would basically take the ABC terms and you translate them into symmetrical components. We're going to have a positive, a negative, and a zero sequence. And then you could actually analyze those three sequence circuits separately, get results, and then transform back into the ABC domain. And we do the same thing here, where basically we're going to apply a transformation to transform the three coupled sets of equations into three decoupled equations. And PSCAD and programs like this do this kind of seamlessly under the hood. You typically don't see the detail, much of the detail what's going on. But this is going to be done through using a matrix transformations, similar to the way we'd have a matrix transformation for symmetrical components. If we were going to assume that these lines were transposed, in other words, that the inductance capacitance matrices had the same diagonal terms and the same off-diagonal terms, where those transposed values would be found by taking averages, just like we talked about before for lumped parameter lines, then there are going to be different transformations that could be used to decouple the equations. One type of transformation is what we call a Karrenbauer transformation. I mean, this isn't the only one. I mean, there's other ones you could use. But basically, what this does is this is going to relate phase ABC voltages to what we call these modal voltages. And this is going to be related by this Karrenbauer transformation given by K. This is going to be a 3 by 3 matrix where this is the form of K, and this is the form of the inverse of K. You could write a similar relationship for current, and once we've got this transformation defined, then what we could do is we can substitute into our three-phase relationships, and we can get a direct relationship between these modal voltages and modal currents, which are going to be given by K inverse times L times K, or K inverse times C times K, or if we're talking about these Telegrapher equations, K inverse times LC times K. In this particular case, what we're going to see for these modal components is we're going to have one term that we a lot of times refer to as a ground mode. The other two modes are going to be line modes, where it kind of turns out the ground mode is similar to the zero sequence, and the line modes are kind of similar to positive and negative sequence in a way. So anyway, if you work in terms of these modal voltages and currents, and you apply a transformation like the Karrenbauer transformation, then what you can do is you can see that these terms like K inverse L times K, they get diagonalized. That you just have the inductances on the diagonal, or you just have the capacitances on the diagonal, or you just have these velocity terms on the diagonal. So if we can do this, then basically this is going to be the equivalent inductance associated with the ground mode. This is going to be the equivalent inductance associated with one of the line modes. Similar for the capacitance, we're going to have speed terms associated with ground mode and line mode, where this ground mode term is going to be 1 divided by the square root of Ls plus 2Lm times Cs plus 2Cm. Okay, so if I take the two equivalent ground mode inductance and capacitances and take the 1 over the square root of LC of that, that's going to give me the speed at which this equivalent ground mode is going to propagate. The ground mode does not propagate as the same speed as the line mode. There's different speeds associated with this, and so this is kind of what makes this kind of hard to do by hand, is when you're doing the math, basically this is going to decouple the equations. So what we're going to have, instead of having a coupled 3 by 3 relationship to worry about, basically it's just like symmetrical components. You know, we could work with the equation for the ground mode as if it were single phase. We can work with the equation for one of the line modes, line mode L1, as if it were single phase. We can work with the equation for line mode 2 as if it were single phase. It kind of like what you can do is you can just solve 3 single phase problems in this modal domain. Then you can just transform back when you're done. So anyway, basically this is just like working single phase problems once you know how to work single phase problems. So anyway, this is just some kind of takeaways on this. So you can see the equations are very, very similar to what we have for doing sequence calculations. So anyway, the way this would work as far as a three-phase modeling is we would have our voltages and currents in terms of ABC. We translate everything in terms of the modal parameters, G, L1, L2. We would have a speed for the ground mode. We'd have a speed for the line modes. We'd have a characteristic impedance for the ground mode. We'd have a characteristic impedance for the line modes. They're not going to be the same. We basically work this through using, say, like pulse balance diagrams for the ground and the two line modes. And then once we had the answers, we convert back into phase values again. So a lot of work associated with this, which is why I'm not going through and having you guys do these types of problems by hand. However, you would still want to do the PS-CAD modeling using this. So I'm going to do another video with a set of worked examples. I've got a couple different cases. I've got one simple case where I've got a surge going down a cable, so I'll work that in a second video. And then there's a second example where we're switching a source. So once you kind of know the fundamentals of how to do one cable, then you can kind of scale this up to more complicated sort of problems. And for both these situations, I'll show you how to set this up in PS-CAD. One other thing I want to mention as far as the distributed parameter line modeling is in EMTP types of programs like PS-CAD, the way this would get done would have to be a way that's compatible with using the trapezoidal rule, where basically we kind of have these equivalent impedances and history terms for current. Without kind of going into a lot of the detail for this, basically the way this works in a program like PS-CAD is you take advantage of the fact that whatever you see on the left-hand side gets mapped over to the right-hand side after a time delay given by tau, where tau would be the time delay it takes for a pulse to go from, say, like left to the right. And so this means that the voltage or impedance times current that we would see on the left-hand side would get translated over to the right-hand side by a delay given by tau. All right, that's what equation 36 says. If you manipulate these terms, what you can do is you could write the current on the K side in terms of a voltage on the K side divided by a surge impedance plus a history term IK, which is a function of what's going on inside M. Similarly, what you could do is you could write an expression for what's going on the M side in terms of the characteristic impedance and voltage plus a history term IM, which is given by 41. All right. So in terms of an equivalent model, what this is going to look like, it's going to look something like this. On the left-hand side, you have the surge impedance, you have the history term. On the right, you got something kind of similar. And then basically all that the PS-CAD model basically does is just kind of models like this line propagation delay. It does the bookkeeping for that. And that's actually what gets implemented in what we would refer to as the Bergeron model. So the Bergeron model is different than the lumped line model. It gives you the ability of modeling the traveling wave effect. One thing you have to add to this still is you have to add the impact of line resistance. And we don't actually model line resistance as distributed. Basically what we do is we still model as lumped. And so the real simple way of doing something like this, where if you had a line, in order to properly model resistance, basically you take this line element and you have a left side, you have a middle side, and you have a right side. And so basically you're just kind of breaking it into um, a left side, a middle side, and a right side. So there's a middle part in there. And then you put a fourth of that resistance on the left side, half of that in the middle, and half of it on the right side. And so you're kind of distributing the resistance in a way, but it's not really just a true distributed parameter model for resistance, but it just gives us a way of modeling the loss effect. And so anyway, there's a lot of complexity to this. Bergeron modeling, this is actually can do some things like at higher frequencies. There's some other sort of characteristics of the Bergeron model. But as far as you're concerned, just kind of keep in mind what PSCAD's doing. It's doing this traveling wave bookkeeping for you, but it's just kind of modeling resistances being lumped in this case. So anyway, I'll go through some PSCAD examples, kind of show you how you can actually make use of the models, and I'll do that in a separate video. Then I'll kind of also show you how you could set this up for doing three-phase as well, based on using a transformation. And then as far as references for this, Greenwood kind of talks about this material, and so this is in chapters 9 and 10. Another book, which is kind of an older book, is a book by Sakis Meliopoulos at Georgia Tech. It's an especially useful reference. It gets into grounding. The Cooper manual, if you can still get a hold of this book, the Cooper Protection Manual talks about this topic. And there's actually, if you go up to the wiki side, there's actually a kind of a nice visual on how reflections, how reflection coefficients work. Okay, so I know this is kind of a long lecture here. They say I kind of expect you to kind of understand somewhat of the basics of the single phase traveling wave analysis, then kind of how to work some of these problems by hand, and then get this mapped into PSCAD. But the extent that you need to work with traveling waves is kind of related to what I'm going to show you in worked example 1 and worked example 2 then.